Lukas Weichselbaum, welcome back to TU Wien, because you were here having some lectures. So he's a senior information security engineer, and we talked about his hobbies before. So he told me that he likes to clean up rivers in Zurich, but not on the surface. He's scuba diving and getting the rubbish out of the river. So
yeah.
Thank you for
if
that.
you want an e-scooter, there's plenty of them in the riverbed actually in Zurich. So
it's an interesting hobby.
Yeah.
So now we're going to hear something about web app security, and Lukas is telling you something about how to use the security features of the new browsers to secure your apps. Welcome, Lukas.
Thank you so much. Kann man mit ohne Speaker aus? Awesome. Thank you and welcome everyone. It's really great to be here today. I have actually been taking a quite long break from presenting at conferences due to COVID. So this is the first one since a long time, and I'm really excited actually to share what has... Yes, thank you. Yeah, but the security world didn't stand still in the last 2 years, obviously, right? And there's some really cool, exciting things to talk about. My name is Lukas. I work at Google Switzerland. I lead a team of like 10 plus people there. And our team is focused on deploying web security features and developing web security features at scale. It's a super fascinating topic for us, and I'm super excited about it, obviously. But we actually get to work with browsers and the W3C to build and ship new security features in the browser that fix certain things in the web platform that are root cause for many security vulnerabilities. And then the other half of our job is to actually take these security features and deploy them at scale across hundreds of applications. So I'm personally a huge fan of not having to ask developers to do security work if we can do it ourselves, right? Would rather have them focus on shipping great products. And the way we are scaling security right now is basically two things. We build in these web security features directly into our core frameworks. So if someone launches a new application or a new product, they basically have CSP, trusted types, other things directly built in, and developers don't even have to know that it's there, right? That's the ideal case. And on the other hand, we also have a ton of existing applications, obviously, that are super sensitive. And for these, we try to backport security features at scale, roll out CSP across hundreds of applications at the same time, which is super fascinating, the problems you run into. So enough about that. Let's maybe jump directly into it. If you have a web application that has authenticated sensitive content, right? You obviously want to make sure that the data is safe, and the web platform, the browser, actually gives you a couple of really handy tools that can help with this. So it all starts with a header, right? Why headers? Because browsers have to be backward compatible, right? They cannot just, as easily as other products, fix a thing and then turn things like security on by default, because that would break half of the internet often, right? So they have to provide these opt-in mechanisms. And then for us, as a security team, we have the challenge of actually deploying these opt-in mechanisms within our application ecosystem. So I won't get too much into detail, but basically there's a bunch of CSP headers here. There is new headers like cross-origin opener policy or cross-origin resource policy, and there's also new request headers, sec4dev headers. They all serve different purposes. Free content security policies is maybe for some folks a bit excessive, but it actually makes a lot of sense. Not all of them are about XSS mitigation. The third one, for example, is an allow list CSP, which is trivially bypassable in terms of XSS. But the third one, for example, just prevents our own developers from sourcing scripts that are not Google controlled, like sourcing third-party scripts, for example, right? But before we talk about these stuff in detail, let's maybe step a bit out, and look at the, web threat landscape first. At Google, we are lucky to have a really good running vulnerability reward program. Obviously, that helps us to fix bugs, but for us as security team, it's also even more interesting because we actually get like these hundreds of bugs that allow us to spot trends and react to these trends with like hardening measures or remediation efforts that tackle some particular root causes of XSS or other vulnerabilities directly, right? So we actually really love having this data of like what type of XSS we're seeing in the wild and what are the other issues. And at Google, the largest amount is roughly web-related issues, which is also the focus of our talk today. And within that, XSS is still a large problem. This slide is slightly outdated, so XSS has been improving since then, but generally that still holds. So I would like to break up this threat landscape into two high-level sections. One is injection attacks, like XSS. I guess most of you have heard about XSS. Just a quick recap. You basically echo back some user input, either from the server side or directly in the DOM. And that user input is interpreted as code by the browser because the browser can often not differentiate what is legitimate code from the server or in the client side from user input. So that leads to a ton of issues. And in particular, for sensitive web applications, this can be like, it's like one of the worst bugs you can have. It's like remote code execution of the web, so to say, right? Like you basically have full control and can fully impersonate the user and, install applications on phones, look at their location, read their emails, right? The consequences are really severe. So that's definitely an area we're putting a lot of effort into. And then the other one is the bucket of insufficient isolation. And I don't know if you have been thinking about it like that before, but it's really interesting, right? Because we have same origin policy, which is meant to isolate different origins from each other. But in certain circumstances, there are some small gaps because of the way how cookies are scoped and others, right? That allow, for example, evil.com to attack victim.example, right? The classical example is cross-site request forgery. You lure a victim on your page, an attacker-controlled page. It has a form. It's submitting the form with JavaScript to another server. And if the victim is logged in there, the browser will send cookies along with that request. And that server cannot tell such a request apart from a legitimate request and will just carry out the action if there are no CSRF protections like tokens. There are other similar issues like XSSI, cross-site leaks, timing attacks, and even newer ones. You probably have heard about Spectre, right? It's getting even more esoteric here because if you focus on web security, you have to take microarchitectural issues in the scope of your threat model, so it does really not get boring. The issue here is if evil.com and victim.example end up in the same process space, the attacker can maybe, within the same process, exfiltrate some really sensitive data that would otherwise be protected by the same origin policy. And these issues are not just Google VRP specific, we obviously see them in the entire industry, right? So I'm hoping to actually share some of the approaches we have taken to, combat some of these problems in the web platform. Many of these security issues really arise because it's like how the web and the internet has been designed. There are inherent design flaws, right? If you think about cookie scoping, for example. And it's just incredibly hard for a developer to rewrite a secure web application from scratch, right? It's not secure by default, the web platform. So we have to work with that. And I have, today I have 4 security features in the browser for you, 2 for the injection defenses and 2 for isolation mechanisms. And I hope I don't run out of time and can talk about all of them. So I would like to start with trusted types. This is a really exciting one. And I'm wondering how many of you have heard about trusted types before, or if it's awesome. Cool. Excellent. Yeah, if I would have given this talk 2 years ago as planned, that would have been a brand new thing, and probably half of you would not have heard about it. I'm really, really happy that you actually have heard about trusted types by now. It's a really promising way to completely eradicate DOM-based XSS, which has become one of the most prevalent subclasses of XSS, and is therefore a really big problem also for the newer web applications, which are very heavy on the client-side code base. Quick recap, how does DOM XSS happen? It's basically the same pattern across security, right? You take a string, you don't know if you can trust the string, right? And that string is passed to an API that can turn string into code. So a prime example is you have this URL with the pink part on the right after in the URL fragment. And in the client side, in the JavaScript or TypeScript code, the code fetches this part and assigns it to inner HTML. What happens is that the browser happily turns this string into HTML code and executes it. Since this URL fragment is user-controlled, an attacker can actually use that to execute arbitrary JavaScript in the context of the user, and you have XSS. So the issue with DOM-based XSS is actually that it's not just one thing you have to review, maybe as a security reviewer. There's like over 60 DOM APIs that can take a string in some form or the other and turn it into code. So imagine modern JavaScript web applications, 100,000 lines of JavaScript code, sometimes minified, and you have to review like 60 plus APIs and trace back if any of their string input ever has been influenceable by a user to actually rule out DOM XSS. It's an incredibly hard task, and this is also why we have so many DOM XSSs nowadays. Because yeah, the ecosystem is moving also towards client side, right? Just like things are built in Angular, React, whatnot today. Classically, like everything was rendered on the server side, and you had much less JavaScript to worry about. It's easier to review. So the idea behind trusted types is, on the one hand, I think ingenious, but also quite simple. You actually block string assignment to all these dangerous DOM-based APIs. There's a ton of other APIs that are not dangerous by default, so to say, right, that you can still use. But the ones like inner HTML, they will stop working if you assign a string to it. However, obviously, there's often still legitimate use cases for for assigning something to one of these APIs, right? Trusted types basically says if you want to do that, you can do it, but you have to first run your code through a policy function that returns a trusted HTML script or script URL object. So you have to be very explicit when you want to assign something to these dangerous DOM-based APIs. How does trusted types work? It's actually quite simple. It is controlled via content security policy, like so many other things, right? And it is actually, basically, as soon as you set this header, the browser will stop accepting string assignments and will basically present you an error. And obviously, it still works, as I just said, like if you have a trusted object instead. So how do you create a trusted typed object? First of all, best situation is if the framework handles this for you, right, and security reviewed. But generally, it's pretty simple. You have a policy function that takes a string, and you basically modify this string in some way, and then you return a trusted HTML or other object. For example, you could invoke a sanitizer, and you would be guaranteed that every string goes through that sanitizer in your application, and there's not some gaps or coverage issues, right? You could also have an allow list of strings that you want to be able to be assigned. Like if it's like a script URL, maybe there is a list of scripts you have, and you can use that. So it's basically up to the developer what to do here. And obviously, if you screw up here, you could still have DOM XSS. But the conceptually really interesting thing here is, first, you force your developers to basically rewrite your application in a way that a lot of the DOM XSS get refactored out. And second, as a security reviewer, you can focus on reviewing this policy function instead of reviewing the entire code base and looking for all these DOM sinks, right? The security critical code is just in this handful of policy functions now, right? That really simplifies the problem for a couple of magnitudes. And even if you don't end up deploying trusted types, you can still run it in report-only mode and get a pretty good idea about like all the dangerous DOM sinks your application is actually using. And you can already start here and maybe refactor some of your inner HTML calls into inner text calls, right? Because often you actually don't even want to assign HTML. It's just convenient, and maybe it was written without knowledge about the DOM sink even being a dangerous one, right? So the benefits are, you really force the flow of critical user data into a very well-defined structure. As a security reviewer, it really minimizes the code base you have to review in terms of DOM XSS. Since these are typed types, right? I think there's also a talk later about type systems, right? And types in languages and why this is a good idea. So this is exactly this principle, right? Like you have types now, and you even have compile time or IDE support for these types, right? So you don't have to wait until the browser yells at you and says it's not possible. You can polyfill trusted types and actually make sure that these types are already used during the development phase. And yeah, if your policy functions are secure and access restricted, you don't have DOM XSS, right? That's the premise. We have tried this at Google and like a couple of hundred applications so far, and it actually worked pretty well. Like we didn't have DOM XSS in a year for these applications. Yeah, so it's a pretty deep topic. There is a blog post by Krzysztof Kotovic about trusted types, which I recommend reading if you want to learn more about this particular topic. Yeah, content security policy. This is like, I think content security policy is just fascinating. It's like this thing that everyone knows, everyone means something different, and it's really powerful, but it's also really hard to get right. And it's like this thing, right? It's like you have tons of different XSS types, and you have tons of different content security policies, and it's really hard to reason which part of CSB is effective against which part of sub-XSS attack class, right? So it's a topic that is generally very hard to convey, and this is also why at Google we try to, have the security team define the policies and roll them out, and don't even ask developers to fully understand this concept, right? I personally really like content security policy because, if you don't have unsafe inline, you really can remove parts of the attack surface, right? A very common XSS subtype we're seeing is JavaScript URIs. Whenever user input ends up in a sink that causes navigation, and an attacker provides like JavaScript alert 1, right? This turns into XSS. If you, for example, have a CSP that doesn't allow unsafe inline, the browser will just never, ever have this part of the attack surface available to the attacker, and the attacker might still be able to bypass the CSP, but they have to look for a completely different XSS vulnerability. And I think that's the qualitative difference, right? And yeah, just for folks who don't know much about CSP, it's basically a very handy tool that allows the developer to precisely control which scripts get executed, and which frames get loaded, and who can frame you, and which trusted types to set or not set, or if unsecure requests should be upgraded, and much more, right? It's completely overloaded, but we're going to focus on the XSS mitigation part of things today. Very important, CSP is a defense adapt mechanism. Do not use a CSP instead of proper escaping, or even if your CSP has fully blocked one of these nasty XSS bugs, right? Even the JavaScript ones, JavaScript-derived ones, you should still fix the underlying bug, right? At Google, when we get the XSS report and is fully mitigated by the CSP, we actually still pay for the XSS report and we still fix it, right? And this is really important to call out here. Like content security policy itself, it's delivered via the content security, like trusted types before, it's delivered via the content security policy header. It also supports a report-only mode. And when people, often when people talk about CSP, this is what they think about, right? And again, there might be a good use case for this type of policy, which is like an allow list, host allow list based policy, right? But generally, this one is really inefficient against XSS mitigation. And I don't know, we have been publishing a ton of research on that topic. There's a couple of bypasses that almost always work for this type of policy. And I also hacked together a tool which is called CSP Evaluator that at least tells you the most obvious issues with your CSP if you have to look into it yourself, right? What we recommend instead is using a CSP that is based on nonces or hashes and doesn't allow list hosts. This policy has a couple of advantages. It has the same structure always, right? You don't have to find all the hosts and risk breakage in production if any of the hosts change at runtime. And it is also much stronger compared to the allow list-based CSP, which can be trivially bypassed. This type of policy still has bypasses in some cases, like script gadgets, in particular in the DOM XSS space. But this is why we generally use this to defend a lot against the reflected server-side stored XSS scenario and trusted types for the DOM-based XSS scenario. However, it still gives you some benefits in the DOM-based XSS case as well, because, for example, not being able to use JavaScript UIs rules out a couple of common XSS vectors. And I also think there's a cool talk about CSP later today as well, which I also recommend dialing in, or, sorry, you're here physically, right? So you can actually just walk there. So for a case study we did in 2019, based on the XSSs we received on like very sensitive domains that had CSP enabled, in the majority of the cases, there was no bypass available. In some of these cases, the strict CSP could be bypassed. For example, there's some corner cases like where you just don't even have to get started with deploying a CSP, which is like, for example, like if you use a Polymer or AngularJS, not Angular, but AngularJS application, because there is like a lot of stuff happening in the framework templates that can be easily used to bypass CSP. But generally, for our cases, the policy has been, quite reasonable in the amount of bugs it has really fully mitigated. Briefly, the idea behind CSP, a nonce-based CSP, you basically put a random number on every script tag in your page response, and that random number is changing on every response. So even if you have an HTML injection vulnerability in your page, the attacker can still inject the script tag, but the attacker, if the nonce is really random, would not be able to guess that value, and therefore the browser will just not execute that script because it's missing the nonce value. And a nonce-based CSP has been around for years, like CSP2, really long time. There's one big issue with it. If you don't control all the JavaScript, for example, like if you load any third-party JavaScript code, like payment integration, Twitter widget, whatever, right? If that JavaScript creates script tags dynamically, it usually doesn't set the nonce, right? And that would just break. So in the past, for large applications that had some amount of JavaScript code that was not fully under their control, that would just not work out, right? Because you can't break the application. So in CSP3, there was a new keyword introduced, which is strict dynamic, which is basically instructing the browser to basically allow already trusted scripts, because they, for example, have a nonce or they are hashed, to create dynamically to create scripts via JavaScript APIs dynamically, and they would also be allowed to work. And with that, you actually can get rid of most of the compatibility issues, and we basically deployed this type of policy across like almost 80% of all our sensitive Google traffic, several hundred applications. So it's much less refactoring work than the nonce-only based version. It has less security guarantees, in particular in the DOM XSS space, but that's often offset, in our case, with a trusted types policy. So what are the steps to deploying a CSP? A nonce-based CSP in particular. First, you want to remove CSP blockers. Why do you have to remove this? Because the browser actually turns off these dangerous patterns in the platform itself, right? So you can also not use these dangerous APIs for your legitimate use cases, right? Common example, JavaScript UIs. As mentioned before, I think that got lost. The right translation got lost when we had the PowerPoint transformation. Anyhow, basically, usually you don't really have to use JavaScript UIs. They are mostly used out of convenience and can really easily be refactored, right? Same for inline event handlers. You can also just remove them and register the event handlers via JavaScript. All of these are actually good practices anyhow, right? It's not just really security related, but once you have done that, CSP can actually disable this part of the attack surface in the browser, and XSS abusing that part of the attack surface would just stop working. Step 2, you have to add nonces to all your script tags. And it's important that you use random nonces, because if you send the same nonce on every page response, it's very easy for the attacker to guess the nonce and just inject the nonce as well. If you use strict dynamic, you're done here. If not, you also have to refactor JavaScript code to propagate the nonce value manually. Step 3, you set the content security policy. Only once you do that, you actually get the reduction in attack surface. So this is a really important step. Depending on your application and how much time you have to spend on, refactoring your application, there's like several levels of CSP, strict CSPs you can use. Again, this is another reason why it's really hard to say, CSP as a whole is broken or not, because it really depends on the actual type of policy you're using. But, all three of these are pretty solid in terms of what they give you in terms of attack surface reduction, right? Obviously, the nonce-only one without strict dynamic would be preferred. But again, you may not always be able to do that. And also here, perfect is the enemy of the good, I guess, right? So a couple of adoption tips. Generally, you can also use hashes. For example, if you have single-page applications, you don't want to use nonces, right? You want to cache them. And in that case, you can, for example, also hash scripts. You can use report sample to make your life easier when rolling out the CSP in report-only mode to get more context about the blockers you had in your application. And in the past, you also had to put some really funky, really funky fallbacks that confused everyone, right? You basically had to add HTTPS and unsafe inline for browsers that did not support the new directives to basically make sure that the application didn't break. So a browser like Chrome, in the presence of strict dynamic and nonce, would just ignore these. In the past, Safari, without strict dynamic support, would have applied the HTTPS value. This is super confusing, right? Because we always tell people don't use unsafe inline. Then we tell them to use unsafe inline for backward compatibility reason. Even if the browser drops that at runtime, it just is terrible, right? So really good news is Safari has shipped CSP3 or large parts of it recently. So you actually can start dropping these fallbacks entirely, and I'm actually really also looking forward to updating my blog posts because I don't have to explain this anymore, which is, yeah, didactically a nightmare. Also here, there is so much more to that topic, right? And there's a nice blog post that, explains the non-space part of CSP to some extent. Obviously, CSP is a huge topic, right? And I don't cover all of it. So what has worked well for us is the combination of CSP, strict CSP and trusted types. Strict CSP for a ton of the classical stored reflected XSS, and trusted types for the DOM-based XSS part. Trusted types only works for DOM-based XSS because it's only a JavaScript focused feature, right? It doesn't help you with stored and reflected XSS. So these two basically really go very nice together. And we had we backported them to about 100 sensitive applications, and they have both, and out of these, we didn't have any XSSs in 2021, which was actually pretty awesome. So, isolation mechanisms, and I think this is a really interesting topic as well, because it's a kind of new thing, and I guess, in particular at Google, we have been busy with XSS for a long time. Since that problem is more solved nowadays, we actually can focus on other pressing issues as well. In particular, in the world where Spectre and Spectre-like attacks become more relevant. And it's isolation issues, right? Like excess search, tab nubbing, login detection, Spectre, XSRF, whatnot, right? So there's two particular attacks that you can pull off in this space. This is like attacks on Windows, and you also have attacks on resources. Attacks on Windows is interesting, right? As a developer of my website, I can basically instruct the browser to not be framed, right? But I cannot instruct the browser to basically not be opened by someone else in a new tab or window, and having that opener remain a connection to myself, right? Retain a connection to myself. So for example, if evil.example opens victim.example, it will still have a JavaScript object pointing to that other window or tab, where it can do interesting things like counting frames, navigating it, sending post messages, and in some browsers, these two will even end up in the same process space, which is an issue for Spectre-related issues. The other problem is every website on the web can embed resources from other websites, right? Which is working as intended. But for example, evil.example could load a JavaScript file from victim.example, and if the user is logged in there, the server will, again, append cookies to that request, and the victim.example server has no idea about to tell apart this request from a legitimate user request, right? So what happens here is XSRF, XSSI, clickjacking, and again, Spectre-like attacks. For example, if a sensitive JSON file or so is loaded in an image tag, it ends up in the same process space, even though it cannot be rendered or accessed by the attacker origin, right? So there's a new security feature that helps with that, and it's really brilliant because it's actually really, really simple and actually addresses a common issue in the web platform itself. This feature is called fetch metadata request headers, and what is happening here is that the browser, when making a request, gives the server more information about the context of how this request was made. So take the first header, sec4dev site. For the very first time, the server can actually distinguish from a request that came from the same origin, like your own site, or if the request actually originated from evil.com and it was just posting a form to your site or loading an image from you, right? So for the very first time, you could, for example, block XSRF by just saying, I would not accept other requests that are not same origin, right? I can say, like, anything that's not same origin, I will just not accept, right? And, that would actually fix a lot of the issues of a couple of root causes of a couple of vulnerabilities we're seeing today. So here's a concrete example. If site.example fetches something in the browser from its own server, that is also site.example, the browser will compare the origins and will say, these are same origin, and will tell the server. So as a server, I can say, yeah, I'm happy to send a response there. If evil.com, for example, does something similar and embeds like the same JSON file in an image, classically, that would just get loaded, and the server would respond with an authenticated response if there's cookies, right? In this new world, the server can actually now differentiate and look at the sec4dev site header and say, I won't serve anything that ends up in a cross-origin environment, right? So I'll just not reply or reply for free or whatever. And that's pretty amazing. And so this is one of the most important ones, but there's also like, for example, sec4dev test that will tell you this is ending up in a script or in a document, right? And you can do really cool stuff with that on the server side. You can basically, having a couple of policies. We call this, for example, a resource isolation policy that just blocks cross-site request forgery, XSI, and other things. While your application, your website will still continue to work, right? And you can do very custom stuff as well. It's really cool. And you can do this in a middleware or in a Cloudflare worker or whatever, right? It's actually really detached from the application. And since it's server-side, you can actually do like a monitoring phase first, basically see which endpoints would violate this policy, right? Have exemptions, and then roll it out safely without breaking stuff. Right now, this is supported by Chrome, Edge, Firefox, and Safari is probably going to ship it very soon as well. I think it's being implemented right now, and once that's happening, you actually can thinking of relying on that not only as a defense and depth mechanism, but really as a first line of defense, because if every browser supports it, you can start relying on it. Might still take some time to fully get rid of your CSRF tokens, right? Because there's a ton of older browsers out there that you may also want to protect, but maybe in a year or two, you can just start blocking traffic from them. It really simplifies a lot of the developer side of things, right? Again, there is a blog post describing a resource isolation policy, which we have also deployed across Google with huge success. And compared to CSP and trusted types, fetch metadata is actually quite easy to deploy. There's like almost no web application side refactoring required. It's really easy to deploy compared to that. Last one, before we go into Q&A, is cross-origin opener policy. This is a new feature that actually helps you to opt out from being opened by someone else in a new window with that other party remaining the opener connection to you. Again, in the current world, evil.example can open a new window, load victim.example, and then can do a bunch of things that often cause security issues. Like I just mentioned them before, but post message, count some frames. Why is that even an issue? Because it, for example, can tell you if the user is logged in or not, right? So it's an information leak. And you can change the location. You load the real login page, and then 5 seconds later, you load a fake login page and hope that the user doesn't notice, right, and enter their credentials there. So that one is also pretty easy to roll out. And it's, again, just a header. If you say cross-origin opener policy, same origin, other sites will still be able to open you, but they will not have this JavaScript object that allow them to mess with your site, right? And some browsers, based on that header, will also be able to separate you from evil.example in a different process, which again is important to prevent Spectre-like attacks. Co-op is supported by all browsers, so that's pretty cool. And if you want to learn more about Spectre, post-Spectre web development, it's actually a pretty complicated topic. Mike West has written a really good article on that as well. Here's the link for that. And yeah, recap. basically, we have a bunch of headers because everything has to be opt-in in the web platform that you can use to secure or make your site securer. And generally, like these 4 mechanisms work pretty well in practice. We have been testing them for a couple of years now, and yeah, give you a good baseline protection against really a large number of common vulnerabilities in the web platform that arise from issues directly from the web platform, right? Yeah, and I think with that we have 5 minutes for Q&A, if my stopwatch is correct. I also want to apologize for the slides. I converted them to PowerPoint, and apparently some of the formatting got messed up with that, because obviously I could not present from my own laptop because projectors are hard, like printers.
Thank you very much.
Thank you so much.
Thank you.
Yeah.
So from my side, the slides look quite good.
Yeah, it was almost fine.
We don't know the comparison, so they were fine, they were beautiful.
Yeah, just small things, you know, but it's really fine.
Yeah, but it could be a lot of design thing too. Like
Yeah, it's modern, right?
Look perfect.
Artsy.
A question from my side, like which of the functionalities, browser functionalities, is like a must use?
A must use. So I think nothing is must use. It really depends on your application, right? If you're hosting your personal blog or some content that is more or less not authenticated and public, I would actually not spend too much time on doing these kind of things and focus your effort on everything that is authenticated and sensitive, right? Like if you have a login page or anything where it's user data, right? These are the things where I would focus my energy on. And mandatory, I guess it depends a bit also what the history of your application is. If you are riddled by XSS, I would focus on CSP and trusted types. If you have more issues on the CSRF side, cross-site request forgery side, I would maybe look into fetch metadata, right? In the end, it's always a question of prioritization and limited resources, right? And generally, strict CSP is also easier to deploy than trusted types. So I guess often starting with the quick wins helps. And yeah, but if I have to make a recommendation, I would say all of that.
Thanks very much. We got a question. Do you have an outlook if browsers will ever ship with a built-in HTML sanitizer? It feels wrong to pull in JavaScript library.
Oh, yes, I can.
A fundamental task.
Thank you for that question, whoever asked it. Yes, there's a sanitizer API that is, I think, spec'd and already landed in Chrome and Firefox. And this is exactly that. You have a browser API that you can use to sanitize things. And it's actually pretty cool because you can even hook it up with a trusted types policy, right? For example, run strings through that sanitizer API directly without having to depend on any third-party code and use like the platform built-in features, right? So yeah, it's called sanitizer API if you want to look it up. I actually wanted to include it, but yeah, not so much time.
Thank you for that question, Tom. Can you come up with the mic for next?
Sure.
And I'm gonna ask the next question, and then the next one is gonna be upstairs. So, what advantage does the sec4dev site header have over the parsing the existing origin header?
Oh, that's an excellent question because it's a very technical one. We would have loved to use the origin header. The issue is it's not sent all the times. So if you start blocking based on values in the origin header, you have a certain amount of requests that per definition never send it. The origin header is mostly sent, I think, for course-related requests, and others sometimes don't send it, right? So this is why we needed to have this in sec4dev metadata. Yeah. And I think that the discussion among browser vendors was that, one solution would be to start shipping the origin header everywhere. But again, that would have caused a ton of compatibility issues because then suddenly tons of servers would actually started to bail out. And so for compatibility reasons, it was decided it's safer to add a new thing again, right? And do it with sec4dev test.
Thank you. So the question from upstairs.
Site.
Thank you very much for the great presentation. I have several questions. So first of all, nonce. So you mentioned nonce as a defense strategy, and it certainly really relies on the randomization framework which is behind. Do you have any suggestions on the framework which should be used and which already hacked?
Yes.
We should not implement because it's already kind of obsolete.
Thank you for the question, and this is like a very important area, I feel, because these kind of things, if possible, should be done by the framework, right? This is the only way to really scale security, and unfortunately, we have a ton of custom frameworks at Google that are not open source, right? So these do that. There have been a bunch of internship projects in the past that were trying to add noncing to open source frameworks. Yep. I think there is a .NET library that does it. That didn't make it into the main .NET repo yet that you can use. I think WordPress, for example, also has noncing support.
Which may be probably already hacked, right? So
yeah, so it's something I wish we would spend more time on as a community, is actually hardening like these open source frameworks, right? And building the security features directly into them, right? So, yeah. I'm afraid I cannot make a good recommendation because I just don't work a lot with open source frameworks these days, and I think my knowledge is a bit outdated, but it's something we can actually investigate and maybe follow up on Twitter or so if you want.
Thank you very much. I have a second question.
Sure.
You just mentioned sanitizer API,
yeah,
which is quite interesting. So is it sometimes this is a very basic sanitizer that you can add. So are you expected that developer using that API should add their own sanitizers? Because sometimes it's just really like fixed one, and sometimes it's really complex that you have to write some code for. Or is it already kind of pre-programmed on your side that you? So
according to my knowledge, Sanitizer API allows you to configure the sanitizer to your use case, like which tags, attributes, etc. There's a good default, obviously. So I think you would be able to replace most of your custom sanitizers, right? Yeah. But I think it also really depends on your use case as well, if it's really possible. I generally see this is important to actually slowly drive the industry towards not everyone builds their own sanitizer and repeats the same mistakes to, okay, there's a web platform thing that is maintained and you can use it for maybe 90% of your use cases. And for these 90%, it works pretty well. And then if someone has an edge case, well, they maybe still have to do something on top of that. But yeah, I guess, again, perfect is the enemy of the good here, right? I guess, yeah.
Yeah, and the last question, if I may. There is trusted types,
yeah.
You mentioned. So it's kind of a basic defense strategy. How does it deal with obfuscation?
With obfuscation, you mean obfuscation of client-side code, like JavaScript?
Yeah, absolutely.
Yes, so generally trusted types is integrated when you're writing the JavaScript code, right? Like when you are in the IDE and you have everything unobfuscated, you actually have to refactor your code to use these trusted types objects. And these can get obfuscated and minified as well if you want to, right? But usually you would not start adding trusted types once the code is already minified, right? So for trusted types, you actually need to have control over the JavaScript code base, which makes it also harder to deploy, right? The Twitter widget example or payment integration, right? If they don't adhere to it, you have an issue. In theory, you can fall back to a default policy where you can define custom rules, but it's getting a bit more funky, and it probably would take another hour or so to go into depth on that.
Yeah, I'm just looking for offensive side also. So it's so difficult to implement on the defensive, so that's obviously it is quite a nice attack surface, right?
And generally the thing that trusted types encourages is like that, entire frameworks like Angular or React, they take on this approach, make their entire JavaScript framework trusted types compatible, right? And then ideally as a developer, that mostly should work unless you pull in some fancy dependencies, right? But yeah, I guess it also really depends on your application, how easy it is to deploy trusted types, right?
Thank you very much.
Thank you for the great questions.
Yeah, thank you for the questions. Thank you for your talk. A warm applause again.
Thank you so much.